For those who don't know who I am, my name is Israel Wachs. I'm professor of chemical engineering, and I'd like to show you, and my primary area of research is in catalysis, and I'd like to show you some application of low-energy ion scattering to catalysis and how just a few experiments have totally changed our whole perception of what's going on in these catalytic materials. To give you a little bit of a background, catalysts accelerate chemical reactions and also control the relative reactivity of the various steps, the reaction pathways, and which by controlling that you can enhance the selectivity, you enhance the reaction rate for the desired product, and try to suppress the steps for the undesired products. Heterogeneous catalysts are solids, and they can be used in gas phase reactions. So you have gas-solid interactions. They're also used in liquid phase, where again they're solids, and so you have reactions between molecules in the liquid reacting at the surface of the solid catalyst. The molecules cannot diffuse into the bulk of the solid lattice, unless, of course, you have something like a zeolite that's highly porous. But generally, the solids are pieces of rocks. Think of it, and the molecules are too big to penetrate the surface. And so the outer surface of the material, of the catalytic material, is of utmost importance in understanding what is going on with the catalytic material and how it's functioning. If you look, the topic I'm going to talk about today is about mixed metal oxides, which are very common in industry. Not only as catalysts, but there are also ceramics and many other applications. The models that, if you pick up a book on catalysis today, the models that people have been using have assumed that the bulk structure, basically, you take a bulk crystal and you cut at a certain angle, like 111, and that's the exposed surface. Bottom line is that they've assumed, since they know the bulk structure from XRD and TEM, they've assumed that the surface is an extension of the bulk. And all the models in this area of catalysis are based on the bulk structure. Okay. So for the first time, we have access to this kind of instrumentation to look what is really the surfaces of these mixed oxides. And this is borrowed from the previous slide, lecture of Hidde Bongsema, that XPS is measuring multiple layers, but with the low-energy ion scattering, we're looking at the outermost surface layer on the order of about 0.2, 0.3 nanometers. Okay. There's another slide that Hidde did not show, but I borrowed from him. So what does that mean? Well, here are two situations, and we can have this one component right on the surface as a monolayer. And if you do ion scattering, you'll only see these atoms here. You will not see whatever the substrate is. If you do XPS, you'll see both, and you won't know if this is on the first layer or the second layer or the 10th layer. You'll still see that, you'll see both components. Other examples are like here. If you have scenarios like this, where you have two components on the surface of a substrate, and if this lighter colored, this gold colored component covers all the blue atoms, in ISS you will not see the blue atoms because you're bouncing off only the top layer. In XPS you'll see both. Okay. There's another situation where you would only see, with ion scattering, you'll only see the outer surface, but not the inner surface. Again, in XPS, you'll see both, and you have no idea which is on the outer surface. Okay? So that's the advantage of doing ion scattering. So let's apply this now to build bulk mixed oxides. So I list here several bulk mixed oxides that are used for various catalytic applications. And this table summarizes the XPS ratios calculated quantitatively for these materials. So here's a material where the vanadium zirconium ratio is 2, and when you go measure the XPS, it says that it's 2. Okay, so here's another material. The vanadium aluminum ratio is 1:1. When you go measuring it, the vanadium aluminum ratio is 0.63, indicating that there's less than there's a depletion of vanadium at the surface. If there's an excess of vanadium or molybdenum, this number will be greater. If there's a depletion, it's going to be lower. Okay. Here's another. This is a very famous commercial catalyst here. This iron molybdate. It's used for methanol oxidation to make formaldehyde. It's one of the top 10 chemicals produced annually in the world. The ratio in here is 3 molybdenums per 2 iron, so it's 1.5. And when you go measure the XPS, it's 1.8. Here's another material, the cerium molybdate. The ratio is 1.5 of molybdenum to cerium. That's the bulk ratio, this value, stoichiometric bulk ratio. The surface, it's higher, indicating an enrichment of molybdenum. And here's some other, also commercial catalysts. These are used to make the monomers for polyesters and things like acrylonitrile, acrolein, and so on. So let's take a look at some of these materials more carefully and see what is really going on when we do ion scattering. So I'm actually going to start with the right side of the curve here. This material, in this notation, is I've actually made close to, not quite a monolayer. A monolayer would be in excess of 8 vanadium per nanometer squared, but I've spread the vanadium over the zirconia. And I have other ways to prove that, which I won't go into right now. And here, what I'm going to do, the experiments I'm going to do are going to be, I'm going to do simultaneous sputtering and ion scattering analysis. I'm going to be basically knocking off the atoms from the first layer and seeing what's below the first layer. Okay? And as a function of time, this is time 0, my first scan. You can see here there's a vanadium signal right there, and there's almost none or very, very weak zirconium. And it is consistent with the fact that I've made a two-dimensional phase of vanadium covering the zirconia substrate. Notice as I start sputtering, the zirconia signal comes up, and because I'm knocking away the vanadium, and here's the vanadium signal. If I take the ratio here of these two peaks, quantitatively integrate these peaks, and I'm plotting here the zirconium to vanadium. Now, at the beginning, if I really did have a monolayer, these data points should go through to the origin, 0, which it almost does. So I have almost a monolayer of vanadium on the zirconia, and the reason this zirconia-vanadium ratio is increasing with the number of scans is I'm knocking away the vanadium from the first layer. I'm exposing the underlying zirconia. But the fact that it goes through the origin or close to the origin tells me that I have initially a two-dimensional layer. So this is sort of my model system. Let's now look at the mixed stoichiometric oxide, which is vanadium and zirconium. And shown here is the first ion scan, and you keep, while you're sputtering, you go and you look at more and more scans. Initially, you can see this is zirconium energy. There's almost no zirconium here, and there's vanadium. Okay, and with time, the zirconium signal is growing, and this is actually getting a little bit weaker here because you're depleting the vanadium. If you do the same thing and you plot the zirconium to vanadium, you have almost going through the origin, not quite. So there's some zirconium initially on the surface, a little bit. But here what's happening is that it doesn't keep growing linearly, it bends over. And the reason is because there's zirconium and vanadium also in the bulk of the material, as well as on the surface. But what this tells us, the fact that it bends over like this, that this is the bulk composition, okay? And this zirconia to vanadium ratio is much, much lower. We have an enrichment of vanadium on the surface. It looks almost like this. So this zirconium-vanadium compound, which people have looked at and in textbooks have shown it to be just a terminating plane with 2 vanadiums per 1 zirconium, is actually almost all vanadium. The vanadium has surface segregated in this material. Here's another example of aluminum vanadate, and here is a model compound where we put 3/4 of a monolayer of vanadium on alumina. And again, you see initially a very strong vanadium signal. And as you keep sputtering and doing the analyses, you can see the aluminum signal comes up because we're knocking away the vanadium oxide in the overlayer. And you plot this data, and it doesn't go through the origin because we only had 3/4 of a monolayer A monolayer is 8 vanadiums per nanometer squared. So we do have a little bit of aluminum exposed at the start, but you can see how it's going down here and sort of approaching this low area of 0. Here now is the compound AlVO4. Okay? The ratio in the bulk is 1 to 1. Okay? And here is the first scan. So you have very nice vanadium signal, very little alumina. As you sputter and keep analyzing, you see the aluminum signal comes off. You take this and plot it here the same way, aluminum-vanadium ratio. Again, you see it bends over and almost goes through the origin. This compound has vanadium monolayer. Even though it's 1-to-1 bulk stoichiometry, the surface has nothing to do with the bulk. The vanadium surface segregates. Here's an example for cerium, and here again is almost a monolayer. It's a little bit low. A monolayer, it's about 75% of a monolayer. A monolayer would be 4.5 moly per nanometer squared, and this is molybdenum dispersed on cerium oxide. And here you have the shoulder here is cerium, and you can see that almost all is molybdenum on the surface, this is a model compound. And when you begin to do the series of sputtering, you can see that the cerium signal comes up, and you can see that the molybdenum signal goes down because we're knocking off the molybdenum overlayer. If you now look at this compound, cerium molybdate, you can see here, you can see a little bit of cerium here, and the band's a little bit broad. With this, I think we'll use helium ion. Could have had better resolution if we used neodymium ion, so neon ion. And but you can see that it's more and more cerium is appearing as you're sputtering away the surface. Again, if you plot this, the intensities here, cerium to molybdenum, you can see that it's almost going through the origin. It doesn't go through the origin because we only have, in this sample, 75% of a monolayer. And here now is the bulk compound. And you can see the same thing again, that it's coming very close to a very, very low value. Also, look at the intensity, the units here. This is 0.05, and 0.05 would be somewhere down here. This material has molybdenum on this compound. On the surface, it's not 1.5 moly to cerium. It's almost all molybdenum on the surface. Okay? It's surface segregated. So using the bulk structure to make a model for how these catalysts operate is definitely problematic. And only doing this surface sensitivity of low energy ion scattering can we actually see the first layer where the chemical reaction occurs. This is the commercial catalyst that I mentioned of iron molybdate. So again, I make my model I disperse 2.3% molybdenum oxide on this iron oxide, which is close to monolayer. And initially, in the first scan, you can see very little iron signal, and here's your molybdenum signal. As I start sputtering, you see the iron signal grows, and the molybdenum stays the same or decreases a little bit. If you take the ratio of iron to molybdenum, you see it's a straight line, goes right through the origin, that we indeed have a two-dimensional layer of molybdenum oxide on iron oxide. Here now is again the first scan here for this sample with almost no, this is where the iron peak would be, and this is the molybdenum. Here is a compound, stoichiometric compound, where it has 1.5 moly to 1 iron, and you still see a little bit of iron signal, but it's mostly molybdenum on this compound. Industrially, excess molybdenum oxide is used, and the reason is that you need to cover, these iron-exposed sites are non-selective. And by having excess molybdenum, you make sure that they're covered. And as you can see, this kind of commercial catalyst, which is stoichiometry is 1.5, it's a little bit higher, it's 1.7, but the iron signal is basically not there. And the selectivity of this catalyst is about 30 to 40% improved over this because the iron sites are non-selective in this reaction. And so you need to have excess MO3. And you can follow by this and know what kind of catalyst you should have to have the right reaction selectivity. Lastly, a very important commercial catalyst is these bismuth molybdates. And here's an XPS analysis. And you see the carbon, and there's a little bit, in these samples, there's a little bit of potassium there. And if you go XPS measuring 10 to 20 layers, if you look at the outer surface of this material, Here's the bismuth. Initially, it's almost no bismuth. In this sample, this is molybdenum, and here's your potassium. So where is the potassium? Well, you can see as you start sputtering and you're repeating the scans, the potassium signal goes away very quickly. So potassium has a low melting temperature, around room temperature, surface segregates, surface diffuses, and it likes to be on the outer surface. And as you knock away the potassium, you can see the bismuth come out. Why this is important is that commercially, this is used, this catalyst, very important catalyst, but the models in the literature use the bulk structure as a termination, and they say that bismuth does this in the reaction and molybdenum does that. But what we found in many samples that we looked at, that were always contaminated with potassium, and that the surface really doesn't even have bismuth or a trace of bismuth. So again, the models in the textbooks are needing revision when you go and start doing this. So only low-energy ion spectroscopy provides the true surface composition of the outer surfaces. And this is for the first time. And the reason that these things were enriched is that potassium impurities, as well as other alkali, molybdenum oxide, vanadium oxide have low Talmon temperatures, which means that they diffuse at very low temperature. Molybdenum at about 300 C, vanadium will start diffusing at 200 C. And usually these materials are prepared at like 500 C. So they have ample temperatures to have diffusion, and they have much lower surface free energies than the other cations in these materials. And so they have a driving force, they have the kinetics to get to the surface, and they lower the surface free energy of the system. So I leave you with this last slide. For this class of catalysis, I think the textbook has to be rewritten, and that this new information is totally changing the perception of how these catalysts operate and what's really going on in these catalytic materials. And I'm sure if, as this technique is applied to other materials, catalytic as well as non-catalytic, it'll begin to start changing people's perceptions of what's going on and how those materials function. So thank you very much for your attention. Be happy to answer any questions.
I don't really understand exactly how you're doing the sputtering, what energies are involved.
I don't have that information in front of me. With the reference at the beginning of the talk, we published this a few months ago, at the end of last year, in Angevant Chemie. And there, that reference here. And if you go here, you can get all the experimental details.
I was curious, the sample you did by XPS, you could not find any bismuth. How this specimen was prepared?
No, it was, of course, it was, I didn't show that region. I only showed the potassium and the oxygen, or the carbon region. It's there, very easy to detect with XPS. Because the XPS is measuring several layers. What we found is that when we sputter these materials, the bulk stoichiometric oxide, they're enriched either in one layer or two layers only. And after the first two layers, it's basically bulk. Okay? It's just you have this surface segregation. The reason that you have low surface free energy is the molybdenum oxide terminates in a double bond. And vanadium oxide terminates in a double bond. Those have low surface free energy. For example, compared to bismuth, that terminates in OH, or iron that terminates in OH, or cerium that terminates in OH. And so that is the thermodynamic driving force. And since we're above their Talmon temperatures, which means that they have the kinetic energy to move, the driving force is pushing them to get to the surface. And so they only surface segregate in the first or two layers. And after that, you're involved. However, the catalysis is in that first layer. And so that's very, very important. Any practical model, any idea of improving these catalytic materials, you have to know what is really at the surface and how you want to then modify the surface. And by the way the community has been modifying, improving these catalysts, if you read the patents, is they just changed the bulk composition, because that's all they had a handle on from X-ray diffraction on the bulk structure. And he tried to correlate the catalysis with the bulk structure. Yeah.
So is it fair to say that the results that you just showed suggest that the role of the other metal, the one that's not segregating to the surface, is really just to tune the electronic and chemical properties of that exposed surface layer?
Right.
So you have two molybdenum catalysts, and whether you have ceria or iron as the underlying metal determines what the catalytic activity
The
is?
electronic properties of the active site for the molybdenum vanadium is determined by who it's bonded to. And that's what we have discovered with many systems. In fact, you can make the same catalyst. In fact, when we took the pure iron oxide and just covered it with molybdenum, it behaved identically to iron molybdenum. And so we already know from other work of supportive metal oxide that the underlying, or the next nearest neighbor controls the electronic properties, electronegativity and electron transfer between that and the adjacent site. Carol.
Yeah, you mentioned about using different ions to get that spectral resolution.
If you have two peaks that are close in energy, like isotopes, you can easily use a different, heavier ion, and that will separate that. So that was actually mentioned earlier a little bit by Professor Brunkstommer. So there's no problem in separating isotopes with any ions. If you have two that overlap, like one example would be molybdenum and tellurium, for example, the problem with helium, you can't separate them, but with neon, no problem. So everything is separate. This can be separated with launch ion scattering.